Hello, my name is Cassiano Gatto, and I'm gonna show you how to use SCAN, Spatial Congruence Analysis in biogeography. I coded in Shiny in our environment, so I'm gonna show you how to run the app from GitHub and how to load maps into the application. And from these shapefile maps, we're gonna calculate a matrix of congruence, spatial congruence similarity, CS. And from these values, we're gonna build using scan algorithm, a network of biogeographical relationships based on spatial congruence and how to use these values of spatial congruence to identify chorotypes and how to use the congruence limits to organize these chorotypes. The GitHub page, see here, we are in GitHub -Cassianogato-scan engine. And here you can see all the files that we will need in this exercise. Most important, we have some rmv. Rmv is a package in R that we will need to install. To rmv, we will recreate the environment that I had 2 years ago when I wrote the code. So it was a distinct R version. And these two files, user interface and server, are the two main files used to Shiny to run the app. And also we have here a scan our project that we can load in RStudio. And briefly, we have here some explanation about what is scan about. Um, Here you have the link to the R42. You can install RStudio if you don't have it yet, and set RT2 as the default version. Okay, this is important. So let's go there. Here we go. These are the two main projects. You can run from your desktop if you download the files or clone the scan engine GitHub folder to your desktop. Or you can uh, run it remotely. You just need to call Shiny, and then you run that code that I never remember. Run GitHub the address. So it's downloading from GitHub now, and chorotypes here, and here the reference to the paper. Let's load the four files required to a shapefile to open. We have to tell our which column holds the information about the species ID. So by default, I use SP. You can change it in your data sheet, in your shapefile, or directly here. You can use the name here. So once we load the map, we can check the columns names, SP and geometry, and all species in the data set are shown here. Okay, so all subsequent analysis will be based on these and only these monkey species distributions. Okay, so we're gonna use the Hargrove index as described in the paper. It always comparing two species, how much they are overlapped, and how much, and of course this is balanced by the area of each species. So area of overlap balanced by area of each species. It's a very nice index. It's a kind of, it's an analogous to the Jacquard index. But it behaves very well. If the species have exactly the same distributions, they have one, a CS, and if they have very small congruences, spatial congruence, the index values are very, very low. So you can check it in the paper also. So let's apply the CS index to the map. So as you saw here, it was very fast. We have SP1, SP2, and for each pair of species, we have a CX index calculated. So we can save these data sheet, which is, it can save you a lot of time later when you go to subsequent analysis. You just hold it, save it in your computer. Okay. Well, here in spatial congruence analysis, we're gonna apply the algorithm, which will organize all these relationships in uh, coherent groups, meaningful groups, especially speaking. And now we have some adjust some settings to do. The first one is very important is the resolution. The scan goes by rounds of analysis. So it starts in a high value of congruence threshold, another very important term. So it's the maximum value of congruent similarity between species that I'm allowing in my analysis, and also the minimum value of threshold. So we have a range of thresholds between, in this case, between 0.9 and 0.4. By the way, we are using comma here as in the Brazilian system. And because we already saw that the minimum congruence we have in our table is 47.47. Here we have a very important criterion is overlap criterion, and it means all species in the groups that will be recognized have to be overlap between themselves, or we are interested in gradients of distribution and transitions. Also, we're gonna allow some species to be related to each other in the same group. You can see in the paper also. Uh, you can I show how distributions can be indirectly uh, informative. Two species can be indirectly connected through intermediate species, depending on the congruence threshold or level you are uh, considering. So all species have to overlap or not. So it depends on you. And here is the size of the diameter of the network. Each group of species is represented by a network. We're gonna see it in the next stage. So 15 is a very large value. Use a, we're not gonna find anything above 4 or 5, maybe, I don't know. So I'm gonna put 10 here just in case. So let's run scan. Well, for a few species, it's fast. Oh, here we go. All these species are configured in groups, meaningful biogeographical entities, core types. So you can see here that these groups have some properties like the number of species, diameter in the network, the maximum CT, the minimum CT, where they are occurring, and other network indexes that I'm not showing detail, and some of them I need to explore further and try to adapt some previous biogeographical provocations and concepts that I developed earlier in those papers to network metrics. So here, for example, we have a group of 4 species that is the same as this other group of four species. They are all the same. But depending on the congruence values we are focusing in the congruence, we are the threshold we are using, the diameter of these relationships change. I will show you later. So all the groups found are here, and we also can save these results as this table. The parameters we can save. Here is the download button. But more important, we can save the graph nodes and also save the graph edges. I will show you now the scan viewer. Here is where is the place when we can visualize core types. We have this option to load previous uh, nodes and edges saved in the step in the scan analysis, but it's already loaded here because we just did the analysis. So these are graphical settings, and you can adjust the palettes or the graph layouts or the alpha of the distributions. And here, the most important tool in the whole app is where you choose the congruence value that will limit the number of species and chorotypes found at this corresponding value. So for example, at 0.9, it's a high value of congruence. We have just one chorotype composed by 2 species, Calitrix geoffroy, Sapajos robustus in the Atlantic forest. So here we have a map, a raw map. Here the network representation, and here we can visualize in leaflet. Okay, so as we relax the threshold, we expect more core types and more species inside the core types. Basically, now we have 4 types, 2 species types distributed all across South America. In point 5, we are having only 9 types again, and we can see here that the Guiana chorotype is just a single unit now because we relaxed the threshold. So both groups that were formed in higher um, congruence are now merged into a single unit chorotype here. And we have the Belém area of endemism now composed by a species directly related at this congruence level. So we have the diameter of the graph diminished, but here we still have a 2 uh, units of distance in the graph. And once we relax more the congruence, we can see that the same chorotype now is related by one step, each species to the other. Well, that's it. Hope you can soon apply the method to your own dataset. Feel free to contact me through the comments below or using my email, cassianogato@gmail.com. And I'm fully available for partnerships and accepting suggestions. And I want to develop more things, both conceptually and also in the code. So maybe we can have a nice app very soon. Maybe translate to JavaScript in Google Engine. So that's it. Thank you very much. See you. Bye.